Hello, everyone. This week, I want to do a sort of combination of a lecture and a lab together rather than doing them separately, and I think this is probably the format I will do in the future. And all I wanted to do this week was give a very short introduction to how you can do some plotting of maps in R and some basic GIS analyses. This is a really highly requested topic that many of you have asked about this semester. It was also asked about in previous semesters, so I wanted to make sure that I could at least cover this in a tiny bit of detail before we finish up the course. Okay, now obviously using GIS and manipulating spatial data is a huge topic, and so we won't be able to delve into any great detail. And what I'm not going to do today is really cover all the nuts and bolts of getting your data formatted, making sure you have the right coordinate systems, the right ellipsoid, the right datum, all that sort of stuff that you are going to need to do in a really formal GIS analysis. I'm not going to delve into that today. But what I want to show you is how you can use R to plot raster data. It's one very common type of spatial data that you're going to want to plot. The other would be vector type data, so like polygons. You can also do that in R, and there's lots of great tutorials online that can teach you how to do that. So I'm not going to get into that today. I want to show you how to plot raster data, manipulate it a little bit, and then extract data from it based on point data. So for example, if you had GPS coordinates of a bunch of different points, how you could pull the data from your raster layer out based on the locations of those points. So this is something that I've done previously for my research. I wanted to figure out what was the landscape composition, the land cover composition in some ecologically relevant distance from a bunch of sampling locations that I had up in the Arctic. So we're going to do something similar today, but with a raster of population density data that I found online. And these comments here are just to keep me on track and make sure I know where I'm going. Okay, so as always, I'll just start by making sure my working directory is empty. It is, but I'll just clear it anyways. And what we're going to need for this is this raster library. So if you don't have it installed, you'll have to install it. But since I already have it installed, all I need to do is load it. So I'll go ahead and do that. It also requires a few other libraries. So when you install it, you might want to specify dependencies equals true. And that will make sure that it installs these other libraries like SP, and I think there's a few others in there as well. So make sure you go ahead and do that. And now I'm going to go ahead and read in my raster layer. So I'm going to sort of try to code this on the fly. There's a good chance I'm going to make a whole bunch of errors along the way, so just bear with me. Okay, so I'm going to read in my raster layer. And what this is just basically a map of population density across the continental US. So I will call it US pop, and I'm going to have this file available for you online on Canvas. So US pop is equal to, and then to read it in as a raster, okay, that basically means that it has pixels associated with certain values for each of them across a certain grid extent. So I'm going to read this in as a raster, and then I read in my file. And actually, I should probably make sure I have the correct directory specified. Okay. So let's go ahead and run that. US pop, it takes a second to read it in, and it is read in. So this raster function is from the raster library. Now what I can do is take a look at US pop. And when I type that function, I get a bunch of information out. So I can see that it's a raster layer class. It tells me the dimensions, how many rows, columns, and cells are in that raster. So it has 720 rows and 1,560 columns. And if I multiply those two together, hopefully I get this number back. Okay, so that's the total number of cells in my raster. It tells me the resolution, which is basically the pixel size. It tells me the extent of my raster, so it goes from coordinates of -125 to -60 on the x-axis, and y is from 20 to 50. We'll see that in a second when we plot it. Here, this is my coordinates and reference system. And in this case, there isn't one attached to this. But normally, you would probably have some sort of coordinate system attached to your raster, especially if you're using like GIS layers or you download some layers from Google Maps. So this is typically where it would tell you what your projection is. So normally, you're probably going to use something like UTMs or NAD83. It'll tell you the ellipsoid you're using and the datum. All that sort of stuff would be contained in this coordinate reference if your raster layer came along with one of those. So like GeoTIFF files are image files that come along with coordinates and these reference systems, so they're ready to plot right away. There are also ways to change these up or reproject your particular raster into whatever projection and coordinate system you want. So we're not going to get into that today. In our case, ours doesn't have one, so it's sort of floating in space off in its own Cartesian coordinate system here, but that's okay. We'll still go ahead and just use it as is. Now, before I get too much further, I should probably mention where I actually got this data set from. So in Google, if you just Google GIS in R, you'll get a ton of helpful information. And so I'm going to go ahead and do that. And the first hit that I got is this GIS in R tutorial. And so it has a whole bunch of really useful tutorials on how to bring in data, how to combine multiple data sets, making maps, etc., etc. The one that I am focusing on today is making maps from raster data. And so I'm using this US population raster file. Okay, and so we're going to sort of loosely follow this tutorial. But I just wanted to point this out so that you know that there's a whole bunch more information on this website, but also other websites as well. So you can get into extremely detailed tutorials online. All that information is free, and honestly, it probably provides much better detail and much more accurate information than I'm going to provide. But sometimes it's nice to actually see someone walk through this process, so we'll go ahead and do that. Okay, so we're going to use the plot function to plot this raster, but what's interesting, and I just discovered this, I'm going to pull up the help file for this plot function. Actually, let me just put it in here. Okay, in the script. So let's pull up the help file. So normally the plot function we've been using all semester long is this just generic XY plotting. It's available in the base graphics library. But when you bring in the raster library, it also offers its own plotting function. And since we've loaded raster, this will now be the default plot function when we want to plot a raster object. So this is actually a little bit different than the plot function we've been using all semester. Okay, it takes a whole bunch of arguments here, and we can actually specify a whole bunch of things. So we could interpolate cells, meaning we can sort of smooth things out if we want, if we set this to true. We can choose the extent of our raster that we want to plot. So if we only want to plot a subset of it, we would specify that with this extent argument. This color argument allows us to define the colors when we plot our raster. Alpha is a transparency, so we could plot several rasters over top of each other with different transparencies, which is sometimes helpful. This col NA allows us to choose the background color. Add lets us just plot one raster over another. Okay, so we might want to use this add equals true along with some alpha for transparency. Okay, so these are all arguments that are unique to this plot function that is specific to the raster library. But let's go ahead and plot USPOP and see what happens. Run that. It might take a few seconds to run because it's a pretty large raster. And when it finally runs, we see this fairly disappointing map. So most of the values here are extremely low, almost white. Personally, I'm colorblind, so I can't even really tell. Like, I assume this goes from white up to like dark red, or maybe it goes through greens or something here. And I sort of see a few little like dark smudges in here. But for the most part, it looks like it's all white. And so that's not especially useful for us. Okay, so one thing that we can do is turn these zeros into NAs and then just try replotting it. So the way that we would do that is we actually want to extract the values of USPOP. So what are the raster values of USPOP? If I just run this function, so I'll hit run, it's going to take a second, but it's this giant matrix of values, and each cell in that matrix corresponds to the value of that raster at that XY coordinate. So it would probably be 0, 0, 0, 0 all the way across for all, like, well, how big was US pop for all 1,123,200 cells in this raster. Okay, so what I want to do is take this matrix, these values of US pop, but what I want to say is for this matrix, this values of US pop, for the ones that are equal to 0, okay, the values of US pop that are equal to 0, let's set that to NA. So we'll just make them NA. Okay, now I can do like summary of the values of US pop. I think this values function, let's actually just check it out. But I think this is unique to the raster. Yep, get values. So this is actually a function that is only available through the raster library, and this just tells you the values of your raster that you're interested in. So let's take a summary of that. I can see the min is 0. That's weird because I thought I specified 0 should be NA. Okay. The max is 374,000, and then I have set 647,000 NAs. Well, that's weird. There are still a few 0.0s. Let's try doing this. For all the ones that are equal to 0.0, we'll set those to NA as well. Well, I don't know why that's not working, but let's just try plotting it anyways. Okay, I can kind of sort of make out a bit better definition here, but that's still fairly unsatisfying because most of the continental US is extremely unpopulated, so it's still very close to 0. It's not quite equal to 0. And then there are just a few areas here along the coasts, along the Great Lakes, that are extremely populated. So one of the ways that we can actually sort of squish all this data together is to log transform it. And what that does is it actually sort of collapses this range into a proportional format. So every unit increase will be a proportional increase or an order of magnitude increase. Okay, so I want to sort of show you how we could do that. So let's call this US pop 2 is equal to US pop. So we're just going to basically copy our original data set. But now what I'm going to do is say the values of US pop 2 are going to be the log scale of the values of US pop 2. Okay, so we'll log transform these values. And what that's going to do is squish everything together into this proportional format that will really allow us to more clearly visualize differences, especially at this really low end of the scale. Okay, so let's hope this works. And now let's try plotting. Plot US pop 2. Okay, that is a much more satisfying graph. So it seems like most of the continental US, again, I might be misinterpreting this because of my color blindness, but I feel like a lot of the continental US is somewhere around 0. And so if we wanted to get what is the true density, we would say exp of 0. Okay, so because the complement of the log scale is to just exponentiate it. We discovered this in module 11. So exp of 0, say most of the US is around 1, has an actual value of 1. Okay, but some of these really highly red areas, I think, would be exp of 10. And so there are some areas of the US that have population densities of about 22,000. Some of these really, really red areas would be more like exp of 13. Okay, so those would be more like 400,000 people per square mile. I'm assuming that that's what this scale is, but I'm not quite sure. Okay, but this log scale allows us to visualize these differences maybe a little more clearly. So that's another reason why you sometimes want to log transform your data. If you have some extreme outliers or a very skewed distribution, so most of our values are close to 0, but we have a few extreme outliers in these really populated areas, log transforming your data sort of normalizes that distribution a little bit and lets you more clearly visualize differences, especially at the lower end of your scale. Okay, now let's try to change the color scheme up here. So I am assuming that this goes from white to yellow and green up to red, which is probably a fairly unpalatable color scheme. So maybe we can do a little bit better. And it turns out that there's this library called rColor Brewer that is specifically designed for map making, and it was actually designed with data visualization in mind. So it has some predefined color schemes that are actually really helpful for plotting. So we'll go ahead and load this library. You may again have to download it yourself using the install.packages command. And then it contains this function called brewer.pal, which is going to create a color palette depending on what we want. So let's go ahead and just take a look at this. So brewer.pal, we want to say how many different colors do we want in our palette or in our gradient. And then what is the name of the palette that we want? And so it actually has a bunch of predefined palettes. So let's take a look at them. Okay, so it actually has qualitative palettes, which are good if your data is categorical. It also has these diverging palettes, which are good if your data is continuous, like ours is. So they can go from like purple to orange. So these tend to be highly contrasting palettes that are actually helpful for people who are colorblind to be able to see them more easily. Go from red to blue. That's sometimes a really nice palette. Let's go ahead and try that one. So let's try the red-blue palette. So I'm going to call this pal is equal to brewer.pal. Let's go 9 colors, and this will be the red-blue color palette. Okay, so pal. So if I was to call this object pal, it just tells me those 9 colors, okay, in this format that R is going to recognize. So R knows what this color is, this hashtag FDDBC7. It knows what that is. And now if I want to go ahead and plot USPOP2, but I can say I want to use my own color palette, pal. Let's see what that looks like. Okay, so that's a little more helpful maybe. You can see there aren't a lot of areas that are red, and there's quite a few areas up here that are blue. Let's try adding some more colors to this gradient. I don't know how many this can actually support. The maximum is 11. Okay, let's try 11 different colors and plot that again. So we get just a little more definition here. Interesting. Maybe let's try another palette. Let's try a sequential palette. Maybe, okay, I think the one they used on the website in the tutorial was orange red. So let's try that. Okay, apparently I can only have 9 colors maximum, so I will set that to 9 and plot it, and let's take a look. Okay, so it goes from white up to orangish reddish, and this is maybe a little more pleasing to the eye and a little easier to identify exactly where on the spectrum we are using this type of a color palette. Okay, now the next task is going to be, let's see if we can zoom in. And so we're going to use the extent argument in our plotting window. And let's just choose an extent that we think is relevant to us. So let's try to take maybe our area of the US over here in the Intermountain West. And so maybe we want to go from like -115 to like 105, and maybe something like 38 up to 45 or so. Okay, so I'm just going to call this extent. And now the way that this works with this argument is we specify our minimum x, so -115, our maximum x, let's go 105, our minimum y, which will be 38, and our maximum y, which will be like 45. Okay, that's our extent. So this is just a vector with those 4 numbers in it. But then I plug that into my plot. I say my extent is equal to these 4 numbers. What have I done? Oh, I did not specify -105. Okay, that's a little bit better. So now my plot only goes from -115 to -105, and from 38 up to 45, those coordinates. So here we see, I assume this is the Great Salt Lake. This little white dot up here, I think, is probably Bear Lake. So we can actually zoom in further. Let's go from -115 only to -110. And let's go from -40 up to 43. From 40 up to 43. 40 to 43. Okay, so this is Great Salt Lake, Bear Lake. Maybe this is like the Utah border right here. I'm not quite sure why it just abruptly transitions in density from here to here. Different census techniques, perhaps. Okay, so this is a way that you can sort of zoom in on specific parts of your raster using this extent argument. Okay, now often we have GPS points that either we have collected out in the field or we maybe randomly generated them and we want to place them on the map so that we can go out into the field and randomly sample this area. So let's do that. I'm going to create 25 samples, so 25. And I'm going to generate 25 random points within this extent and plot them on this map. So to do that, I'm going to just create a data frame. I'll call it df is equal to data.frame. So I'm creating a new data frame. My x is going to be, I'm going to draw from a uniform distribution. So with equal probability, I could get any value between -115 and -110. And I want to draw 25 samples from that. So my min is going to be -115. My max is going to be -110. So if I was to just run this without putting it in my data frame, I get 25 random draws with equal probability from anywhere in this range. And then I'm going to do the same thing for my y coordinates, runif 25. But in this case, I want to draw between 40 and 43. So my min will be 40, my max will be 43. So let's take a look at my data frame here. So now I have 25 points where I have a random x and a random y from within this square, or that rectangle, I suppose. Now if I want to plot that, I'm just going to use this points function. So this just overlays points on a plot. And my x is going to be df $x. My y will be df $y. What plotting character should I use for this? Normally 19 would just be solid black dots. But I don't know, let's try. Let's see what point character 1 is. And let's leave them black. So by default, they're black. Okay, let's try plotting this. It's rounded circles. Those are pretty hard to see. Let's try 19. I'm used to using 19. Plots black circles. Okay, so there's 25 random ones within this extent. Okay, I'm actually going to bring my plot. I'm just going to paste it again in front of here. So now if I was to rerun this a bunch of times, you can see that each time I rerun it, it regenerates 25 new random points from within that extent. So once I'm satisfied that I have a good sample of the area, that looks pretty good. Now I might want to say, okay, well, at the location of each point, at the exact location of each point, what is the raster value that that point is sitting on? And so I can do that with another function from the raster library. So the function I want to use for that is the extract function. Let's just take a look at the help file for extract. Extract values from raster objects. So what do I need to provide? I need to provide the x and y coordinates that I'm going to extract. Oh no, that's not correct. Okay, I need to provide a raster object as the first argument, x. The y argument says points represented by two-column matrix. Okay, and that's going to be my x and y coordinates. So let's try this. Extract. My raster object is called uspop2, and then the coordinates, the points represented by a two-column matrix, is going to be df, because again, df is my two-column matrix, x and y. Okay, so let's just run this and see what happens. Okay, now for each of my 25 points, I have the raster value associated with that point. And so you can see that a couple of them have fallen on NAs. So these are probably these ones right here that happen to fall in the middle of the Great Salt Lake. One of them has fallen just on the edge, and so actually just barely hit a different raster value. And maybe I want to plug that into my df data frame. So I could say df.vals is equal to extract. So now if I was to take a look at my data frame, I have my x coordinate, my y coordinate, and in the third column, I have the associated raster value that is exactly at the center of where that point is located. Before moving on, I realize I made a programming mistake up here. So you'll see up here I set samples equal to 25, and then I intended that to sort of control the number of samples I was going to draw and plot on the map. But then I manually specified 25 in each of these arguments. So what that means is that if I was to change this, let's say all of a sudden I wanted 50 samples, and I rerun all of these lines, it's still only going to draw 25 samples because 25 is hard-coded into here. So what I should have done was set this to samples, which is the number of samples I want. Now I could set this to 150 samples, and if I rerun this code, it now plots 150 samples. Or I could change it to only 5 if I want. Okay, so this is what I mean when I say that you should try to avoid like hard coding your scripts and maybe try to make them more flexible wherever you can. So samples controls the number of samples here. I only have to change one number here. I don't have to change it twice manually in each of these arguments. But okay, let's just set it back to 25 where it was, and we'll rerun this. Okay, so I'll just run this. Okay, I have my head of df. Okay. So this extract function, I should also point out, is really cool because one of the things that you can do with it is you can actually specify a buffer around each point. And so you can say that you actually don't want to just extract a single value corresponding to exactly that xy coordinate, but you can actually specify a buffer around each point and say, I want to extract all the values, all of the raster pixels from within any distance you want from each point. And so that can let you calculate things like the average landscape or the average raster value from within a certain circular radius. You could calculate diversity indices. So what is the diversity of pixel values that you find in there? You can calculate the variance or the standard deviation of pixel values or the median. So this starts allowing you to, get much more flexible and interesting spatial statistics by changing the arguments of these type of functions. So the last part of this, maybe we want to conduct an analysis. So maybe we want to know whether when you move from left to right, does the mean population density change in any predictable way? So let's just say if we move from east to west, we want to know, does the density increase or the log density? So what we could do with this is, now that we've extracted the pixel values from each of these points, we can plot them as a function of x. So we could go plot vals as a function of x, data is equal to df, because we've stuck this vals into our df data frame. Let's plot it. And we don't really see any really obvious pattern here. Let's just make these points darker. There's nothing really obvious jumping out here. It looks like the variance is increasing from left to right. And so if we wanted to, we could use a linear model, LM. Let's just see if the values increase from left to right. Okay, we have a slight positive slope here. X as a slight positive, but let's see if that's statistically significant by pulling up our summary table. And that p-value is extremely high, so that is not a significantly positive slope. So we would actually say that there is no significant trend from left to right. We could plot the line of best fit. We would do that like this. And so even though this line has a slight positive slope, it's not statistically significant. Let's see if there's a significant increase in density from these random points we've sampled as we move from bottom to top. I'm guessing there probably won't be. So now we'll just change this to y. Does the raster value depend on your y location? Again, there's nothing really super interesting going on here, although we do have this weird sort of like high variance on the left side of our graph and low variance at the top over, or on the right side over here. Let's see. Okay, we have a not significant, a highly non-significant trend, so that's no change in the mean density from top to bottom or bottom to top. We could plot our line of best fit, and it's pretty much perfectly flat. So this last part was just to show you how you can use some of these spatial points, and you can actually do like a statistical analysis. So again, just to recap, what we did is we loaded a raster. We zoomed in to a particular area we were interested in. We generated a bunch of random points across that landscape. We extracted the values of the raster from each of those random points. And then we conducted just a really simple, probably silly linear regression to see if the density, which is what this raster represents, does population density change from left to right? Does it change from bottom to top? And we found that in both cases it did not, because the p-value was extremely not significant. So you can delve much deeper into these types of analyses. I highly recommend that you spend some time, if this is the kind of thing you're interested in, looking at tutorials online. So there's a ton of really useful information out there. And the great thing about R is that all of these packages are open source and free to use, and there really are no barriers to learning this on your own. Okay, well, that's it for this week. If you have any questions, definitely post them in the discussion board and we can try to answer them. There won't be any assignment this week, and so all you're going to have is the final quiz of the semester. And then next week, we will spend a week just reviewing the course material very broadly. And then we'll move into the final assignment, which you'll have 2 weeks to complete. And that will cover all of the material that we have covered throughout the course and basically just be a chance to refresh on all of the things that you've learned over the last 13 weeks. All right, have a great week, everyone.